let's dig in a little bit and talk more about the core of effect. So, I know about like effect types from a lot of functional programming ecosystems. And so, effect has this type called effect, which is like the sort of core fundamental primitive. It's like to make error handling more robust, but it also has something that's different from some of the other types in the ecosystem I've seen. So, for example, I've used never throw, which is another sort of functional effect-based library for just doing error handling. Right? It's like don't throw, return a result type, and it has some stuff on there. So the core effect type has this like success and error generics built into it, so it feels like a result type, like you might see from Rust or from Neverthrow or whatever. But it also has this like requirements generic, which is kind of interesting. So to bake in like kind of what the effect depends on. Can you talk a little bit more about like that core type and its usage, and like why is having dependencies like expressed as a part of the types of the effect? Like, why is that important?
Yeah, no, that's a very valid question, and we get that question quite a bit. Why is the effect type represented the way it is? Maybe we can start by talking about like, you know, any program pretty much that we ever write has three concepts, right? It has inputs. You put inputs into the program that you're going to run, right? Whether it's a CLI or a binary or whatever, that program's going to have some inputs. And the effect type sort of represents those as the dependencies of your program, things that your program needs to run. And then when your program actually executes, it can either succeed with something or it can fail with something, right? And those three things are kind of core proponents of any program that we ever run. And so that is kind of the logic behind why the effect type is designed the way that it is. It's designed to represent a program, right, that is going to be run. And that type goes back to other libraries from other ecosystems. Effect was originally very heavily based on the Zio library from Scala. So a lot of these ideas are not our own. They're ideas that we took and sort of adapted to work really well in TypeScript. But that's kind of the reason why the effect type is structured the way that it is. It's designed to represent a program. And an effect that you declare in your code is exactly that. It's a program, but a program as a value. So when you actually declare an effect in your program that you're writing, nothing actually happens when you run that file, right? The effect is lazy. And because it's lazy, it's a lazy representation of a program. It allows us to do some pretty cool stuff. You can modify the behavior of that program at runtime. You can add behavior. You can wrap it with additional things that you need. And it gives us some pretty powerful things that maybe we can talk about later related to concurrency and like observability that we can do that you might not be able to do very easily, or if at all, with kind of like a JavaScript promise, for example. So maybe like an easy way to conceptualize an effect is like a lazy promise. It's a promise. It's a program you've declared, but haven't run yet. And then in order to actually execute that effect or program, you have to run it with something. So you would actually execute it in code, and that kind of runs the effect. So it's kind of like the basics of like why the type has three generics and why it's structured the way it is. But getting back to your question about why expressing a program that way is so important, the having errors and dependencies explicitly declared in the types of your program, I think is a extremely valuable thing to have. Right? There's a whole RFC that exists in the TypeScript repository about adding throws clauses to TypeScript in general, right? Because clearly developers want a way to express the fact that their program might fail with some reasons or for some reason, right? But JavaScript's not really designed to support that kind of like typed failure paradigm. So that's why libraries like Neverthrow and other libraries like that exist, is to kind of support that particular use case. But with effect, we also take it one step further and also represent the requirements of your program, the things you have to put into the program to make it run in the type as well. So what do I mean by the requirements in this case? Well, programs in general have aspects of them that you want to isolate and be able to test, right? The the there are many aspects of our program that need to be tested, and oftentimes it can be difficult to test if they're not isolated into their own pieces of logic. So with effect, we represent those dependencies, those pieces of logic that we want to kind of inject into our program in the requirements channel so that we can, in a type safe way, say, hey, this program needs a database. We don't care what kind of database it is, but it needs a database to be able to run. So we put that in the type so that if you run if you declare your program and don't provide it with a database, you get a compilation error. And declaring dependencies in this way comes with like a couple of different benefits. One is the testability of your program dramatically becomes a lot easier because you can plug in whatever version of a database from our example before that you want. So in production, maybe you're using like a Postgres version of implementation of that database, but in testing, maybe you have like some test version that just mocks out everything that you need. So being able to have that represented in the type system makes it really easy to see at a glance when you're working with effect how this program can succeed, what it's going to produce if it succeeds, what errors it could potentially fail with, and then what dependencies it needs to actually run. So both making your program much easier to understand at a glance, but also making it much more easy to test because you can inject whatever versions of a dependency you want in order to satisfy that requirement at runtime.
So you're doing a lot with the TypeScript type system. You guys are pushing it probably as you said, beyond what it was meant to do. So have you guys tried like experimenting with changing that type system in any way or like contributing back to TypeScript to get some of these things going?
Yeah, no, there have actually been several different experiments that we've done over the years with TypeScript as a type system because personally, I believe TypeScript to be one of the most powerful type systems that exists. Being able to have essentially a programming language as a type system is an extremely powerful thing that I think is undervalued in the general programming community. I think TypeScript is an amazing language. And we did an experiment, I think it was about a year ago, primarily led by Mike, our kind of like the benevolent dictator for life of the effect community. He led an experiment where we forked the TypeScript compiler and built something called TS Plus, which was a way to add behavior and generate runtime information, but from the type system. So for example, you could declare a type in your project and everything was annotated with kind of JS-doc annotations. So you could annotate a type that you declare in your type system to register it with TS Plus. And then you could add behavior to it. So you could, for example, declare like, I don't know, a map function. And then in JS-doc annotations, you could attach that to the type that you've declared so that instead of making that type a class and declaring everything inside the class, which becomes totally untree shakeable, instead at runtime, it just figures out that exists and you still get the nice auto completion. Like if you were to run that as like a class. But he also took it a step further and added support for custom operators that you could declare. So you could overload, for example, like the plus operator in with these JS-doc annotations. So you would register like, I forget what the annotations were called. It was a while back, but you could register, for example, a function to a operator. And then when you actually compile TypeScript, it would replace instances of those operators in your code with that function call, which was kind of cool. We also had derivations So in other languages like Rust and Scala, you can do metaprogramming with derivations for different things. So we added support for that to TS Plus, where you could declare a type, like an interface, for example, and then you could use a derive macro to generate a schema for that at runtime, which was kind of like pretty cool and something that hadn't been done before. And TS Plus actually led to some PRs back to the TypeScript code base after finding like issues and things like that. But ultimately, while TS Plus was super cool, and at a certain point in time, we had replaced all the effect code in the code base with TS Plus code because it compiled to TypeScript, so it didn't matter. The problems with TS Plus is that obviously it required a compilation step that did not play well with other tooling in the JavaScript TypeScript ecosystem, because many of those tools, just strip types, don't do a compilation pass. So for example, if you were using this TS Plus in anything that required hot module reloading or just stripped types in general, you would end up with a problem, right? And the other problem with TS Plus is that the compilation step was long. So just like compiled languages that have long compile times, we introduced a compilation step that took a really long time. So that was kind of like an experiment that we did a while back, just to try to make it easier to work with TypeScript types and add metaprogramming to TypeScript, because that's obviously not a core proponent of TypeScript, is that it has to work with JavaScript. But again, ultimately we abandoned that experiment, and Mike actually wrote a great blog post about TS Plus, kind of like a post-mortem on that project, and why it was great and why it sort of like fizzled out. But we've also worked closely with some of the contributors to TypeScript over the years. So Matoush is like probably one of the most avid contributors to TypeScript that we know. And we work closely with him when features come up that either are bugs or things that are missing from TypeScript that we want to add. So either we create PRs ourselves, or we work with Matoush since he's so much more familiar with the code base. But yeah, I mean, there's always going to be features of TypeScript that we miss, that we want access to. But overall, I think that, like I said in the beginning, it's one of the most powerful type systems on the planet, and I don't really see how other type systems can catch up, because being able to again program with types is such a powerful paradigm to have access to.
Yeah, for sure. I think it's probably best for the ecosystem that you drop the experiment. And I think the biggest thing is like the thing that I think about is like with any new tool is like what are the implications for adoption? And I think like effect as it's landed today with this sort of like logical structure that it has is obviously really powerful. But it's already a hard thing, I think, sometimes to convince people is like, yes, this does a lot. You should buy into it and you should use it, you know. And if it was like, oh, and also there's this other like fork version of TypeScript that does all these things that you like need to use it, it would have made adoption a lot harder. So I'm glad y'all took a different path with it.